that kidney can regulate. You know, GFR, which is intrinsically a kidney parameter. Does that make sense? And blood pressure, which is a systemic. So what we're going to talk about is GFR versus blood pressure. Okay? And just like with, I don't remember, what was that? What did we talk? Oh yeah, blood flow through the tissues. Think of it this way. Remember we're talking about the regulation of blood flow through the tissues. We discussed that when everything systemically is fine, so when systemically everything goes well, then GFR, kidneys maintain GFR constant. Does that make sense? If blood pressure drops or increases, like in the long run, if systemic problem occurs, then whether or not GFR is maintained is not important. So regulation of blood pressure is more important than regulation of GFR. If blood pressure is fine, then kidney is going to focus on GFR. If blood pressure is not fine, they're going to focus on blood pressure. So let's talk about GFR maintenance. There are two mechanisms here. The first mechanism that allows you to maintain GFR is myogenic mechanism. So in myogenic mechanism, and if you think about blood pressure, listen, if you think about blood pressure, it changes, right? Like you exercise, it goes a little bit up, like you chill, it goes a little bit down, so there are fluctuations. So essentially the whole idea here is to shield GFR from these changes in the blood pressure. So when blood pressure goes up, right, GFR increases. We were talking about the net filtration pressure last time, NFP, how net filtration pressure depends on two hydrostatic pressures, capillary and capsular, and osmotic pressure. Since capillary pressure, capsular hydrostatic and capillary osmotic are pretty much constant, the only one that actually changes is capillary hydrostatic pressure, basically blood pressure. The higher blood pressure, the more filtrate is formed. Now, we need to slow it down. When blood pressure increases, the blood vessel stretch increases as well. Does that make sense? Now, in response to that stretch that is detected by mechanoreceptors, afferent arteriole constricts and efferent arteriole dilates. Does it make sense? So what essentially happens, the arteriole that feeds into the glomerulus becomes narrower. The arteriole that drains the glomerulus becomes wider. And as the result of it, the hydrostatic pressure, capillary hydrostatic pressure, decreases in the glomerulus, right? And net filtration pressure decreases, and GFR decreases. Does that make sense? You can sit closer if you want. Does that make sense? Now, obviously, when blood pressure decreases, the entire thing, you just flip all the arrows, period. And you flip the effects on this one. So, in case of decreased blood pressure and decreased blood vessel stretch, afferent arteriole dilates while efferent arteriole constricts. Okay? Now, another mechanism that allows you to regulate GFR is called juxtaglomerular. So in this case, I'm gonna put some stuff in perspective here. Trying to see if this model will work. This one will. Oh God, this is some big model here. So here, see glomerulus, right? So it turns out, and if you look at the organization here, you can see that the convoluted tubule, the tubular system, at some point passes very closely to glomerulus, next to this afferent and efferent arterioles. So that's going to be afferent, and this is going to be efferent here. See that? Mm-hmm. So this is kind of a complex here. You have glomerulus, you have two arterioles, and you have a tubule. Make sense? So it turns out these things, the tubule, the glomerulus, the arterioles, they kind of linked to each other. There's a system of 3 types of cells. So you have, I'm going to introduce those cells. You have macula densa cells. Okay. These are sensory cells that sense the concentration of sodium chloride. Oh, Jesus, here. So they are about here, in the tubule. Then you have glomerular cells. They do release renin, but they kind of smooth muscle cells. They surround the arteriole, the afferent arteriole. And then you have mesangial cell, responsible for communication between macula densa cells and glomerular cells that surround this arteriole. Okay?
So those 3 cells make the complex between?
I don't think there's a special name for this, but they functionally, yes, they make a so all 3 of them will be crucial for juxtaglomerular mechanism of GFR regulation.
Okay.
Does that make sense? Awesome. So what we're going to start with, it really doesn't matter. We're going to do the same. Basically, I'm going to do increased blood pressure. It's going to be a lot of steps. Okay? So make sure that you have some, because I want to go very granular in explanations. So blood pressure increases, okay? So the result, GFR increases as well. Now, by definition, glomerular filtration rate describes the amount of filtrate produced in 1 minute. So if GFR increases, filtrate volume goes up as well. Now you're trying to squeeze more filtrate, more fluid into a tube. The only way you can do it is to increase the rate at which filtrate passes through the tube. Does that make sense? So filtrate flow rate increases. So filtrate is moving through the tubular system faster. We have discussed before, we didn't discuss the mechanism of reabsorption, but we discussed the idea of reabsorption. So taking ions and small molecules out of the filtrate back into the blood. Now, reabsorption happens in the tubules here. So this is the filtrate at the normal blood pressure, right? And this is the filtrate at the higher blood pressure. Faster, moves faster. Now when filtrate moves faster, how does it change the time for reabsorption?
Decreases.
Yes, excellent. So reabsorption time decreases. So since now kidneys have less time to reabsorb sodium from the filtrate, this is like 2 out of 10 question. Since there's less time to reabsorb sodium from the filtrate, what happens to sodium concentration in the filtrate as the result of it?
It would stay the same.
There's less time to take sodium out of the filtrate. What I'm saying is compared to normal,
so it would increase.
yes. So compared to normal, concentration of sodium in the filtrate goes up. Good? Macula densa cells. Look, what is their role?
The sodium chloride concentration.
They sense it. And afferent arterioles constrict. Makes sense, right? Since
Which
they
will slow the volume down.
So afferent arterioles constrict, blood flow through glomerulus decreases, so GFR decreases. Does that make sense?
What increases the flow rate? Like how does the flow rate increase?
Here,
Yeah, like
this
what,
step.
what makes it go faster?
You're trying to squeeze more water in the same tube.
Okay, so just
It has
the
to.
amount of pressure.
Yeah.
Okay.
It has to. You see? And this kind of, well, I'm kind of jumping a little bit ahead of the train, but if you think about it, this is what, like, have you tried ever a famous chicken sandwich from, I think, KFC when they replaced 2 buns with 2 pieces of fried chicken? You may have heard about it. It's the most disgusting meal ever. So it contained double daily dose of sodium in one sandwich. So chicken was not in the middle. Chicken was instead of the bread.
Okay.
Okay, got it? So a colleague of mine ate this thing and said that he had a spike in blood pressure. So what essentially happened? His sodium in the blood skyrocketed, which meant, bypassing all of it, sodium in the filtrate skyrocketed. The macula densa cells, they still work, so they sense it. They send the signal through the mesangial cells to the glomerular cells to constrict afferent arterioles. GFR goes down, which means you start producing, less urine. We'll get to this, it's sodium. You start producing less filtrate, right? You're peeing less, which means you're keeping it in, which means your blood volume suddenly increases. You have a spike in the blood pressure. Make sense? So this is why basically high sodium diet results in elevated blood pressure. And when you have chronically elevated, if you some members of my family who really like salty food. You end up with hypertension. Okay, make sense? Good?
Yep.
So that was for GFR regulation.